In this lesson, we're going to explore some properties of the second derivative. When it comes to describing the shape of a curve, it's certainly important to know whether the curve is increasing or decreasing, but we also need to know how a curve is bending. To describe whether a curve is bending upward or downward, we have the concept of concavity. And when it comes to drawing curves, which is eventually what we're going to get to, what happens is there's actually not a whole lot of options. We have lines that could be increasing, decreasing, constant, or vertical. There's a few options there. But when it comes to curves, we actually only have 4 different types of curves. And those curves can be described through whether they're increasing or decreasing, or concave up or concave down. So let's take a look at the 4. So the first type, increasing and concave up, could look something like this. So in this particular type of curve, what we would have here is a curve that's increasing. So for x values that get larger, so for x increasing, the y values are increasing. So y2 is larger than y1. So we have an increasing curve. But it's also what we call concave up. So concave up basically means that the curve looks like part of a parabola facing upward. That's what we mean by concave up. Whoops. Okay, and because this one is increasing, we would know that the first derivative is greater than 0, so that is an important aspect here, but it's increasing and concave up. So that is 2 different aspects that make this curve what it is. One other thing that's interesting about a curve that's concave up is that the curve, so this is 1, 2, 3, so the curve lies above its tangent lines. And to show you what that means, if I pick some point on this interval and I draw a tangent line to the curve at that particular point, on this entire interval where I'm concave up, the curve is entirely above the tangent lines. So that is an aspect that we have of curves that are concave up. If we compare that to curves that are increasing but concave down, now this curve looks more like a parabola that's facing downward. So you can kind of say that it's opening downward, okay? Or if you imagine a point on this curve and you draw its tangent line, the curve itself lies below the tangent lines, so that makes it concave down. But this is a different type of curve than the one above because it is increasing. The y values are getting larger from the first x value to the second x value, but it's concave down. So increasing and concave down. The next option are functions that are decreasing. So if we look at a part of a function that is decreasing but concave up, if we note the x and y values, as x increases, the y values are getting smaller. So it is decreasing. But if we draw a tangent at any point here, the curve lies above the tangent. So therefore it's bending upward, and therefore it's concave up. And lastly, we have curves that are decreasing and concave down. So this is decreasing in y value, but it lies entirely below the any tangent line on that particular interval. So those are the only 4 types of shapes that we can have to curves. And what we're going to learn later on is how to put those together to make generalized functions, but for now, just know that these are the options. Let's look at an example here to help us understand this relationship between concavity and its tangent lines. Okay, so here I have the graph of a function, and I can move a point along that function and look at different tangent lines for this particular function. Now, if you compare the curve to the tangent line on this particular point, the curve is lying below the tangent line. So on this interval, our curve is said to be concave down, which should make sense because if you draw in a parabola, this part of the curve looks like a downward facing parabola. And that's what I said was one aspect of a region that is concave down. Okay, so if I look at all the places where the curve is below the tangent line, okay, still happening here, still happening here, it turns out that there is a place, this particular point, where half the curve is above, half the curve is below. Then if we continue on, the curve then gets to be above that tangent line on the remaining part of the interval. So there's this change that happens. And if you look at this part of the graph, you could actually consider this looking like an upward facing parabola. But there's this point where this change occurs. And that's an important point when it comes to concavity. So we have on the interval from negative infinity up to 0, we have that entire interval is what we call concave down. Because that interval looks like a downward facing parabola and the curve lies below its tangent lines. Then we have on the interval from 0 to positive infinity part of a curve that is concave up, because the curve looks like an upward facing parabola and it lies above the tangent lines. But there's this one special point right here at 0. So where x equals 0, or if we want to be more precise, we can call it 0, 0, because it really does happen at a y value. And at that particular point, what's happening is we have a change in concavity. So our graph changes from concave down to concave up. And anytime we have a point that our graph changes concavity, that's called an inflection point. And those are important points for us when it comes to drawing graphs. So it's good to be able to visualize what that means. Here's another graph that we're going to work through, and this is the graph of x to the 4th minus 2x cubed, so the next example that you should see on your page. Pause the video, try and identify the intervals of concavity and the locations of inflection points, and then we will check it together. Alright, so the intervals of concavity. If I look at point P over here in this first little region, the curve is entirely above the tangent line. So on this interval, I have a curve that is concave up. So it's looking like a parabola. But then I have this point right here that the curve now, one part of it lies above the tangent and one part lies below the tangent. So we have x equals 0, or the point 0, 0 is an inflection point. And the interval from negative infinity up to 0, we just stated was concave up. All right, if we continue on, the curve is now below my tangents. So on this interval, over to, it's looking to be about right here, which looks like I'm at x equals 1. So x equals 1 is another inflection point. And on this curve, if you plug 1 into the original function, you should get negative 1 back out. So 1, negative 1 is the other inflection point. Okay, and on that interval, from 0 to positive 1, we were concave down. And then going from x equals positive 1 onward, I now have my curve entirely above the tangent line, so now I'm concave up again. So on the interval then from 1 to infinity, we are again concave up. Now, what you should say in the end is to combine the regions that are concave up, so these two different intervals, make it from negative infinity to 0, and then use the union symbol to join two sets together. So then from 1 to infinity, on that interval, we are concave up. And you don't need to do that for the concave down because there's only one interval there. Okay, now let's pin down what's meant by a point of inflection. So a point of inflection is a point on a curve where concavity changes. So we've established that through looking at curves, but how do we know where that happens? Well, it turns out that this occurs where the second derivative is equal to 0 or the second derivative is undefined. And we know these are inflection points because, as we saw, the graph crosses the tangent line at these particular points. So let's take a look at a function, and let's identify where the graph is concave up or concave down and locate any points of inflection. The way that this is done is we first look for points of inflection. So we're going to get the second derivative, set it equal to 0, and solve. But the other thing that the second derivative tells us is what the concavity of the curve is, whether it's concave up or concave down, depending on if you evaluate an interval at a particular point, just a point on the interval is what I mean, and you get a positive number or a negative number. It tells you, the second derivative tells you if your curve is concave up or concave down. So that's the important part of the second derivative, is its relationship to concavity. So using the first and second derivative, we can describe all different types of curves. The first derivative describes how the curve is increasing or decreasing. The second derivative tells us if it's concave up or concave down. And that's enough to draw any type of curve that we can run into. So, to determine where this is concave up or concave down, the first thing that we need to do is find the second derivative, but we can't find the second derivative until we find the first derivative. So we'll begin there. This would be 2x minus 2, and my second derivative is just the constant function 2. Since this is always 2, what that means is for any value x that I put into this function, my graph is going to be concave up because this number 2 is always positive. And if you think about it, that should make sense because the graph here is effectively a parabola. So no matter what this parabola looks like, the leading term coefficient is positive, so it's going to open upward. It's just a parabola opening upward, which is a curve that's concave up. And it's always concave up. It doesn't change concavity. So because the second derivative is always positive, what we can say is the curve is concave up on the interval from negative infinity to positive infinity, and there are no inflection points. In order to have an inflection point, we would have to have a point that we could solve for in the second derivative. Let's look at another example. Determine where the function y equals x to the fourth minus 4x cubed is concave up or concave down, and locate any points of inflection. Alright, so to do this, we need to find the second derivative. So the first derivative would be 4x cubed minus 12x squared, and the second derivative would be 12x squared minus 24x. And that we can simplify by factoring out 12x, which leaves me x minus 2. So I have two zeros of this second derivative. If I set my second derivative equal to 0 and solve, I get that x is 0 and x equals positive 2 as potential inflection points. All right, it doesn't have to change concavity here, but these are points where it possibly could. So, to test it, it's just like in the first derivative test. We take our potential points of inflection, put them on a number line, and we test using the second derivative. So the intervals are from negative infinity to 0, 0 to 2, and 2 to positive infinity. We just need to pick a value within each of these intervals. So negative 1 sounds great here, positive 1, and 3. So these are values that exist within each of these intervals. And now we just need to test and see what the second derivative says at each of those values. So the second derivative evaluated at negative 1 would be 12 times negative 1 times negative 1 minus 2. So this would be negative 12 times negative 3, which is positive 36, but it doesn't matter so much what the number is. It's just that it's positive. That's all that makes any difference at all. And because it's positive, that tells me that I am concave up. And I don't need to really write that in as long as I understand the interpretation that if the second derivative is positive, that it's concave up. At positive 1, this would be 12 times 1 and multiplied by 1 minus 2. So 12 times negative 1 gives me a negative number. So on that interval, I would be concave down. And then lastly, at 3, 12 times 3 minus 2, this would be 36 times 1, which is positive 36. So I'm concave up over here. So at each of these points, they were inflection points because I changed concavity. And my intervals of concavity look like this. So I am concave up from negative infinity to 0, and then again from 2 to positive infinity. So anytime you need to join two sets, just put the union symbol between them. Then I am concave down on the interval from 0 to 2, so just in between those two endpoints. And lastly, I have inflection points. Where x is 0. And if the problem specifies to answer these as points, make sure you give both the x and y. If it just indicates that it wants the x values, that's okay. If you're not sure, you can always default to giving the point, and that's not bad. That's never a bad thing. All right, so if I plug in 0 to my original function, because I just want the y value associated with it, it's 0, 0. And then when x is 2, then I have to do 2 to the 4th minus 4 times 2 cubed, which is negative 16. And you can use a calculator there if you like to come up with that. Next up, determine where the function g of x equals 5 over x squared plus 1 is concave up or concave down, and locate any points of inflection. So again, what we need to do here is find the second derivative, set that second derivative equal to 0, find out if it's undefined anywhere, get any potential points of inflection points, and then test and see what happens. So our work here is probably going to be wrapped up in getting that first and second derivative, because it looks like, well, if I rewrite g of x as 5 times x squared plus 1 to the negative first power, I can at least get the derivative of this using the chain rule as opposed to using the quotient rule, which is a little bit more time consuming. So let's see what happens with the chain rule. So coming up with the first derivative of the function g, I'll bring the negative 1 down, so negative 5 times x squared plus 1 to the negative second, but then completing the chain rule, I have to multiply by the derivative of the inside part, which is 2x. So that gives me negative 10x over x squared plus 1 quantity squared. So that wasn't too bad, but now I need a second derivative. And the second derivative in this case is going to require the quotient rule. So let's get started. So the second derivative of g, let's see, I need to come off to the side. The numerator is negative 10x. The denominator is x squared plus 1 quantity squared. So the derivative of negative 10x is negative 10. The derivative of this part is 2 times x squared plus 1 to the first power times 2x. Yeah, I'm running out of space there, I understand. Sorry about that. I need to multiply these two parts together first, and I'll come down a line just so I make sure I have plenty of space. Negative 10 times x squared plus 1 quantity squared minus, and then I need to multiply negative 10x times 2 times x squared plus 1 times 2x. So let me kind of do some things together. All right, so it's minus, the negative 10 is going to make this a positive 10, but then I have 10 times 2 times 2, so this is actually 40. I have two x's in there, so 40x squared, then times x squared plus 1. So a little bit of extra work there. Help me get a head start on simplifying. Then that goes over the original denominator, and that original denominator gets squared. So this becomes x squared plus 1 squared to the second power, which becomes to the fourth power. Okay, now we have to simplify. The reason that we have to simplify here is because if I need to find the zeros of this function, I want this thing as simple as possible. Otherwise, it's going to make my algebra that much more difficult. So here's a thing that I notice I can do here, is factor out x squared plus 1 from the numerator, which would leave me negative 10 times x squared plus 1 plus 40x squared. over that denominator of x squared plus 1 to the 4th power. The nice thing about that is this term, x squared plus 1, cancels out one of these here, leaving me with just x squared plus 1 to the 3rd in the denominator. That's a little bit better. Improvements are improvements. If I distribute the negative 10 into this set of parentheses, I will have negative 10x squared minus 10 plus 40x squared all over x squared plus 1 cubed, which looks like I could turn into 30x squared minus 10 all over x squared plus 1 cubed. And I could probably factor out that 30 and make things, well, I'm sorry, not the 30, but the 10. And that's probably about it. So this would make it 3x squared minus 1 all over x squared plus 1 cubed. Great. Now I have my second derivative. So this thing is my second derivative. So a lot of work in finding that, but let's now figure out where things can happen here. All right, so possible inflection points. These things can occur when the second derivative is equal to 0 or the second derivative is undefined. I have to consider the undefined part here this time because it's possible I could have division by 0. Now, remember all your work from rational functions out of college algebra. The thing that's important there helps us here. It's that in order for this function to be 0, we only have to find out where the numerator would be 0. So if I take the numerator, set that equal to 0, that's going to give me locations of where the function is 0. So where 3x squared minus 1 is 0, or 3x squared equals 1, so x squared equals 1/3, or x equals the plus or minus square root of 1/3, which means x equals plus or minus 1 over the square root of 3. So those are potential places where I could have inflection points. Now, where the second derivative is undefined, what happens here is it'll be undefined where the denominator is 0. So x squared plus 1 cubed equals 0. All right, solving this, I would take the cube root of both sides to get rid of that cube. So x squared plus 1 equals 0, or x squared equals negative 1, or x equals plus or minus I, which is the complex value I. What that means is this doesn't have any zeros in the real number realm. We can ignore this. So that's not anything we have to worry about. So the potential places for inflection points occur at positive, negative, 1 over square root of 3. Now, to determine if these are inflection points, we have to use a number line and test. So I'll put negative 1 over root 3 here, positive 1 over root 3 here, and then I have to determine some test values on each of these intervals to see if I'm concave up or concave down. And it would probably be nice to know what 1 over the square root of 3 actually is, so that I can kind of estimate to what values I need to use within my intervals. So that's about 0.577. So something that's a little bit less than negative 0.577 would be negative 1. Between negative and a positive number is 0, and then I could use positive 1 over here on this interval. So that gives me the test values to use. and I need to go through and determine if my function is positive or negative on each one of these. Now, since I already have my calculator out, I think I'll just take advantage of the calculator. So the original function is this. So I have 5. Oh, I'm sorry, I don't want y values. I do want the second derivative. I need to evaluate this at the second derivative. So let me go back to my second derivative, which is 10 times 3x squared minus 1 over x squared plus 1 cubed. Now, I could have put the numerator and denominator in an extra layer of parentheses, but I know from the order of operations that that's not necessary. However, if you would have added those, it would be fine. You'd get the same results. Let me check my table settings. That's great. And I'll go into the table, and I just want to evaluate this second derivative at a couple of points. And it looks like I've actually already got the ones that I'm interested in. -1, 0, and +1. So I'll just delete that one. So at 0, this evaluates to a negative number. At 1, it evaluates to a positive number. And at -1, it evaluates to a positive number. So that's all I need to know. Now I can say that my function is concave up on the interval from -infinity to -1 over the square root of 3. If you rationalize that denominator, that's perfectly fine. You end up with negative square root of 3 divided by 3. Or if you leave it as is, that's fine as well. All right, and then union from 1 over square root of 3 to positive infinity. Then I am concave down on the interval from in between those points. So try that handwriting again. -1 over the square root of 3 and +1 over the square root of 3. And then I have these inflection points. So my inflection points are at, let me just grab the calculator. My function is 5 over x squared plus 1. And if I start evaluating this at those couple of points to get the y values, it should come out as an integer, so it'd be okay to use the calculator here. 1 over the square root of 3, 3.75, and if you need to make that a fraction, show you a secret here, 3.75. If I hit math, the very first thing that comes up is frac. Send it to a fraction, so 15/4. All right, and it also works out that if I put in the negative inverse of root 3, that I get the same value. So it's 15/4 for each one. So I have inflection points at -1 over the square root of 3 and 15/4, and +1 over square root of 3 and 15/4, and these are both inflection points. Now, if that had ended up being like 1 over root 3 and 2 over root 3, then that function that sends things to fractions isn't going to help. Then you just have to kind of go through and just work out the answer using the function and a little bit of algebra. But to save time, that's what I'm doing here. Okay. Now, before we go forward, I actually want to go back a little bit to the very first opening slide here. I want to help you make sure you understand what's happening with the second derivative and why it's related to concavity. And it's kind of difficult to really explain, but I'll do my best here. So here's the thing. When you are looking at a derivative, you're getting tangent lines. The slopes of those tangent lines, if they are positive or negative, tell you if the original function is increasing or decreasing. So a function's derivative tells you if the original function is increasing or decreasing. Now, let's write that down. So f prime tells us if the original function f is increasing or decreasing. Okay? Now, the second derivative. The second derivative is just a derivative of your first derivative, so the relationship is the same. So the second derivative tells me if the first derivative is increasing or decreasing. Okay, now, if you're looking at whether the first derivative is increasing or decreasing, how that relates back to the original function is this. It tells you if the original function is increasing at an increasing rate or decreasing at an increasing rate, or potentially increasing at a decreasing rate or decreasing at a decreasing rate. There's 4 options. Those 4 options are explained in these particular curves. So if you're increasing and concave up, that means your first derivative is greater than 0 to be increasing. Concave up means your second derivative is greater than 0. Concave up means that you are increasing at an increasing rate. So if you look at this curve over here, it is going up in value, but it's getting steeper. So as it gets steeper, that means that it's increasing at an increasing rate. So that's what makes it concave up. Whereas in this next curve, we're increasing, so the first derivative would be greater than 0. We're concave down, which what I'm explaining is the second derivative is less than 0. And since the second derivative is less than 0, then what happens is my function is increasing, but it's not increasing as rapidly. So it's kind of slowing down here. So it's increasing at a decreasing rate. And that's what gives it that shape of the concavity. If we are decreasing and concave up, that means the first derivative is less than 0. Oh, stop it there, smartboard. The first derivative is less than 0, but the second derivative is greater than 0. So you can be decreasing at an increasing rate. So this curve is steeper as you decrease. And then lastly, decreasing, which means your first derivative is less than 0, concave down, which means your second derivative is less than 0. So then you're decreasing at a decreasing rate. All right, let's discuss what's known as the second derivative test. Second derivative test, its objective is the same as the first derivative test, to label relative extrema as either minimums, maximums, or neither. But it uses the second derivative to do so instead of the first. So if we let x equals c be a critical value of the function f, so if x equals c is a critical value, let's just say I have a function like this. This is f. All right, if x equals c is a critical value, okay, I'll pick this particular point here. I know that the first derivative was going to have a horizontal tangent line there. Okay. Now, if the second derivative evaluated at that point is less than 0, so what that means is if the second derivative at that point is less than 0, that would be an interval that's concave down. So that's more like this point over here. So let's pick this point. If the interval is concave down, as it is here, so around this point, my interval is concave down. It looks like a downward facing parabola. That point has to be a relative maximum. Similarly, if the second derivative happens to be greater than 0 at that point, then you're on an interval that looks like it's opening upward, like a parabola, opening upward, and therefore that would be a relative minimum. So it's just using the concavity in order to label that rather than the increasing versus decreasing. There is one catch to the second derivative test, however, and that is if the second derivative evaluated at that point is equal to 0, then the test fails. And that can occur, but it's just one limitation of the second derivative test. You can always default back to the first derivative test if the second derivative test fails. Now you might be wondering, why does the second derivative test sometimes fail? And the reason is, if the second derivative evaluated at any point is larger than 0, then you're concave up, which means that you're at a critical value, or at any point, sorry, if your second derivative is greater than 0, you're concave up, and therefore your curve is entirely above the tangent lines. Well, if your curve is entirely above the tangent lines, then on both sides of that critical number, your curve is above the tangent lines, which the second derivative test can then deduce that if it's above the tangent line on one side, above the tangent line on the other, you've got a minimum. Or if you're entirely below, as in an interval that's concave down, then that means that the second derivative test can then tell that you have a maximum. However, if you have a critical value that just happens to be an inflection point, the problem with that inflection point is the curve happens to be above the tangent line on one side and below the tangent line on the other side. And that's a problem for the second derivative test because it can't really tell if that's supposed to be a minimum, a maximum, or neither. It just doesn't have enough information to be able to determine that because the concavity is just too flat around that point. But you can always revert back to the first derivative test to find out what's happening there. Identify the relative extrema of f of x equals x to the fifth minus 5x to the fourth. And we're going to use the second derivative test to do so. Now, the second derivative test, where I need to begin is getting first and second derivatives. But since I'm testing for relative extrema, I need to stop and get the critical numbers from the first derivative. So we'll get the first derivative, which would be 5x to the fourth minus 20x cubed. And if I set that equal to 0, it would give me my critical numbers. So I can factor out 5x cubed, it looks like. That would leave me x minus 4. So my critical numbers are x equals 0 and x equals 4. So I have x equals 0 and x equals 4. Now, if the second derivative test doesn't fail at either one of these, then the thing is, I don't really need to draw out a number line. If it happens to fail, then I have to go back to the first derivative test, and then I have to draw out a number line. So effectively, the second derivative test might save me from doing the whole number line and testing thing. So let's see. So the second derivative test, of course, requires me to get the second derivative, which in this case would be 20x cubed minus 60x squared. Now, if I factor out 20x squared, that would leave me with x minus 3, it would appear. Okay. Now, I'm going to use this to determine whether or not these values are minimums, maximums, or neither. So if I take 0 and plug it into my second derivative, it's going to be 20 times 0 squared times 0 minus 3, which is 0 times negative 3, which is 0. So there the test fails. We'll have to resort back to the first derivative test for it. But let's try out the next one. If we can get a little bit of information, that's definitely going to be helpful. All right, so the second derivative evaluated at 4 would be 20 times 4 squared times 4 minus 3. 4 squared is 16. 16 times 20, I think, is 320. It doesn't really make a whole lot of difference. The result here is a positive number. All right, I think it ends up being 320, but it doesn't really matter. It's a positive number. So that tells me, since the second derivative is positive, that I'm on an interval that is concave up, so 4 has to be a relative minimum. All right, so 0 and 4 are the points that I'm interested in. I've already determined that 4 is a minimum. Second derivative test told me that just fine. But that also tells me a little bit about the intervals surrounding 4. In order for this to be a minimum, I have to be decreasing on the interval prior to it and increasing on the interval after it. So I have to go from decreasing to increasing to have a minimum, which means my first derivative, I've already got some of these intervals done. It's negative on this interval, positive on that interval. So I really only have to do one test value here. So if I take, say, -1 and plug that into my first derivative. All right, my first derivative evaluated at -1. Let's see, it would be 5 times -1 cubed times -1 minus 4. -1 cubed is -1, so -5 times -5 results in positive 25, but again, it's really only that it's positive that makes any difference at all to us. So here we go from an interval that is increasing to an interval that is decreasing, so this should be a relative maximum. All right, so what I've learned is that the point 0 something and 4 something, I'm going to get those y values in just a second. At 0 something is a relative maximum, and at 4 something that is a relative minimum. And it didn't have to do quite as much testing, which is helpful. It's better when the first derivative test doesn't, or the second derivative test doesn't fail. But the the y values that go along with these points, if I plug 0 into the original function, that's also going to be 0, because 0 to the 5th minus 5 times 0 to the 4th is 0. If I plug in 4, I'm just going to get the calculator and get that. So I'm plugging in 4 to the 5th power minus 5 times 4 to the 4th power, so negative 256. Let's take a quick look at the graph of this function and see that this all meshes and plays out as we expected. At the other point, the second derivative fails, and oftentimes the second derivative test will fail when your curve is on one side of the tangent line and then the other, so you have an inflection point. It can also fail when you have a very flat portion of the graph, and that's actually what we're seeing here. Is the curve is very flat, and so it's not really increasing very quickly around that point, and the second derivative test has trouble determining if the curve is entirely below the tangent lines or if it's above the tangent lines. Here's another example that's pretty common. Sketch a graph of a function with the following properties. F of 0 is equal to f of 4, which is 0. F prime of x is greater than 0 on the interval from negative infinity to 2. F prime of 2 is 0. F prime of x is less than 0 on the interval from 2 to infinity. And the second derivative, f double prime of x, is less than 0. This can seem kind of mind-boggling at first, but we take these piece by piece and put them together, and we really can produce a graph without much effort at all, as long as we understand the properties of the derivatives, first and second, and put them all together. So first things first, let's start with right here. F of 0 is equal to f of 4, which is equal to 0. What that's telling me is the y value of my function evaluated at 0 and the y value of my function evaluated at x equals 4 is 0. So these are points that lie on the x-axis. So we're done with that particular statement right there. We don't have to do anything else with it. All right, let's move on to the next few statements. They involve the first derivative. So let's do a number line. We have something important about the number 2 here. And the reason that I know there's something important about it is because the first derivative is equal to 0. So that tells me that this is a critical number. So it's either a minimum, a maximum, or neither. So we're going to try and determine what that is based off of the intervals surrounding that point. So if the first derivative is greater than 0 on the interval from negative infinity up to 2, that means I am increasing, so my first derivative is positive. So I'm increasing, and then I reach a critical number, and then so I'm done with that, and then I have my first derivative less than 0 from 2 to infinity. So on this interval over here, my first derivative is negative, which means I am decreasing. So what that means is it looks like I have a maximum at 2. All right, then the second derivative, I am told the second derivative is entirely negative. So that means for the second derivative, everything is concave down. So we probably should have an additional point, but we don't, but that's okay. Let's suppose here that f of 2 is 4. Okay, so that f of 2 being at 4 is this particular point, which is a relative maximum. My curve is entirely concave down, so I know that this is going to look like a parabola. And that's a pretty decent sketch.